Okay, good afternoon, everybody. Welcome to the 12th lecture in CFD. And as I was just saying before, today we will continue with numerical methods for nonlinear conservation laws. In particular, we will look at high-order schemes, so not just second order, not just first-order schemes, but also second-order schemes, and then also look at the effects that change it from one order from first order to second order, what changes that has in terms of the appearance of the solution. And I will demonstrate that also with a MATLAB code. And then we will look at stability so that we can understand a little bit how to adapt all the concepts from stability that we developed also to nonlinear problems. Essentially, we will look at linearization of our equations so that we can essentially use the methods for the linear equations. But before I start with the new material, I think I'll do a summary of what we did 2 days ago. Essentially, it's what is written here on the screen. So the first thing that we did last time was to introduce the CFL condition. CFL, that stands for the names of the 3 authors of the paper from 1928 when this was discussed. So that's Courant, Friedrichs, and Levy. And essentially they said that a scheme is a convectively dominated scheme is stable if the domain of dependence of the finite difference scheme contains the domain of dependence of the partial differential equation, so the physical domain of dependence. And if we now do that for the example of an advection equation, for the advection equation, you know that the domain of dependence is just a straight line, the characteristic, the one and only characteristic. And then we ask for this characteristic to live inside kind of the triangle or the shape that is created by the nodes of the finite difference scheme. So that means for the forward time backward space scheme, we'll kind of get this triangle here. And if we look at, for instance, the forward time central space scheme, we would kind of get this triangle. So that means for the characteristic that I have noted here, so an A that is positive, both of these schemes now would be stable when it comes to the CFL condition. What we have, however, also seen is that the CFL condition is only a necessary condition, not a sufficient one. So that means it is not clear that now in this case, both of these schemes are actually stable. And as we have proven then via the von Neumann analysis, it turns actually out that only the forward time backward space scheme is stable, whereas the central space scheme is not stable and is actually a scheme that is unconditionally unstable. So there is no combination of delta t and delta x that makes the red scheme here stable. The yellow scheme is stable as long as the red characteristic lies inside the triangle, so that delta t and delta x and a are such that the CFL number or Courant number, which I can also write down, so the sigma a times delta t divided by delta x, if the Courant number is lower or equal 1 for the forward time backward space scheme. So this was the CFL condition. And the second thing that we talked about last time was the method of the modified differential equation as yet another way of determining stability of a specific discretization. But not only stability, you can also gain more insight into how the solution or how the leading error of the solution would actually behave. And we realized that the method of the modified differential equation essentially is to look at the differential equation augmented by the truncation error. So the first leading error term is then the truncation error that we have derived a few weeks ago already. And if we do that, and if we write up the equation, so the original partial differential equation and the leading error term, we then see what the actual equation is that we are in fact solving, instead of just the green bit, which is the one that we wanted. And in this particular case, for the forward time backward space scheme, again, we see that what we actually solve is an advection diffusion problem with a specific diffusion, a specific viscosity, which is given here, which then leads to diffusive effects. As typical, the viscosity is then the prefactor in front of a second derivative. And what that would mean, if you now just think of what an advection diffusion equation would give as a result, if we plot it here for a specific initial condition that we subject to the advection equation, and then we see that we get something that looks probably like the blue line here. So we have a translated initial condition, so the translated top hat shape, but all the edges are kind of smoothened because of this diffusion. We will see, as I said, we will see later an example where we illustrate that in more detail. But what I would like to say here is that this is actually a very typical behavior for a first order scheme. So first order in space and time, where I discretize the time and the space derivatives with one-sided or first order derivative. Then typically what happens is that the leading error term will be of second order. So in this case, one can then say that we probably can, or we can then translate it in such a way that we get a second derivative there. And if the leading error term is then a second derivative, then typically we get a diffusive behavior. And of course, we also now understand directly why we can use the shape of this numerical diffusivity as a way of determining stability, because we know that a diffusion constant, or a viscosity in this case, needs to be positive for actually creating this smoothening effect. As soon as the viscosity is a negative number, you would actually get an amplification of small errors. I mean, you would have the inverse heat equation, as we discussed, well, maybe 2-3 weeks ago. And of course, that is then a problem that is not stable. So therefore, we can directly see that the stability for condition for stability is that this numerical dissipation needs to be positive. And here we can directly see this number is positive if 1 minus sigma is positive, which again renders sigma to be maximum 1, as we have now seen with other ways as well. Okay, so this was the summary from last time. Are there any questions or things that you wonder about? Because I would like to directly continue with this problem here. So I would now like to motivate how we can actually create schemes of higher order, or what happens actually if you do schemes with high orders. So I do an example. It's example number 2, I think, higher order schemes. Well, how would I do that? So now I have here the example, and maybe I can just well, no, okay. So I have so how would I create the higher order scheme? So let's just start with the forward time central space scheme. So that would technically be a scheme of higher order. So ujn plus 1 minus ujn divided by delta t is minus a divided by 2 delta x of uj plus 1n minus uj minus 1n. So this here is a scheme of higher order, but we know it's unfortunately an unstable scheme. So the problem here is, which we can directly see if we look at the modified partial differential equation. So we look at the truncation error, we get the following. It is ut plus a times ux. And then what we get is minus a squared delta t divided by 2 times uxx. So this here would be the leading error term for the forward time central space scheme. Central space scheme is second order in space and first order in time. Now, what you directly see here is that this diffusion coefficient, so the numerical viscosity, is clearly is a negative number. I mean, it's minus a squared times delta t divided by 2. A squared is clearly positive, delta t is positive, we have a positive time step. Of course, that together with a minus gives a negative number. So numerical is clearly lower than 0. And I mean, that's what we derived last time with the help of the or in conjunction with the CFL condition. So this is unconditionally unstable. Negative diffusion. Okay, now this is nothing new. I mean, this we knew, but what I would like to do now is to try to make this scheme actually stable. Why do I want to make this scheme stable? Well, I want to make this stable because this is second order in space. So I would like to have a scheme that actually is more accurate in the spatial discretization. So I would like to start from this one and make this one stable. So how do I do that? Well, we see that the problem why this one is not stable is because our leading error term has this shape. So we need to somehow make sure that this leading error term can be removed. So therefore, what I'm suggesting now is that we take the forward time central space discretization, but I add something there that actually makes this leading error term disappear. And then we see what happens. So the principle is like this. However, let's add a term to cancel the leading error term. Well, how do we do that? Let me first start with writing up what we already have, which is this one, minus a times 2 delta x, and then we had uj plus 1n minus uj minus 1n. So this is what we already have, but now we need to add something that addresses this yellow term. Well, what can we do? We just add a term that cancels this one, and of course, nothing easier than just trying to discretize exactly this term using central differences. So what I do is I just add here with a plus because here's a minus. So a squared delta t divided by 2 as a factor, and then I do a finite difference discretization of the second derivative. So delta x squared, and up in the numerator I have uj minus 1n minus 2 ujn plus uj plus 1n. So this is the prefactor, and this here is just a finite difference approximation of the second derivative. And of course, what is clear is that the first order term of what I just wrote here will be, of course, exactly the same as the leading error term of my modified partial differential equation. So that means with this, I have certainly canceled that term. The question, of course, is what then happens to the next error term, which then appears, whether this one will be stable or unstable. But what I have certainly done is to remove this lowest order error term. And of course, it would not work, or it would be strange if I show you this scheme if it doesn't turn out to be actually a stable scheme. And yeah, as it turns out, this is a scheme that is called the Lox-Vendroff scheme for the advection equation in this case. And it turns out that this scheme is second order in space. And if you do the analysis, you will also see that it's second order in space and in time. So by doing that, we have also managed to cancel the lowest order error term in time. So this is a scheme that is well known, and people are using that for the simulation of these type of equations. And we will also see it later in the demonstration where I also have implemented. And again, the motivation of how we have derived it is actually quite simple. We have just tried to make sure that the second order term, the leading error term has disappeared. Now, of course, I can go there and do an analysis of this scheme and also calculate what the modified partial differential equation is for the Lox-Vendroff scheme. And actually turns out that it looks like this. If you want, you can try that at home. So it's a ut plus a ux. That's the original equation. And then we have a times delta x squared divided by 6. And then we have sigma squared minus 1 times uxxx. So the third derivative. And then you have some higher order terms. And well, sigma first is the same definition as before, a times delta t divided by delta x. And the stability is given that this is stable for sigma lower equal 1. Okay. So now this was kind of a nice way of just arriving at a scheme of higher order. And the resulting scheme is actually quite an interesting scheme. And let's just analyze that for a second. So first of all, it is a higher order scheme. As you can see, the leading error term looks like this. So it's a delta x squared in there. So the leading error term is of second order, which makes the scheme of second order. Compare that again to where do we have it? Here, to the truncation error of the forward time backward space scheme, where the leading error term was a delta x. Now we have delta x squared. So that makes the scheme to converge, or the error for the same grid spacing is of course smaller. And of course that's a good property. We have a higher order scheme. That's one important aspect. So we can write that down. So we have higher order. The second thing is it's actually a scheme that is symmetric. So my stencil here is central differences in space here for the first derivative, but it's also central differences in space for the second derivative. So that means I do not have an upwind scheme. So it's not doing upwinding in any direction, not from the left, not from the right. It is like the forward time central space scheme. So it's a central scheme. And of course, that's very good, because then I don't need to care in what direction my convection goes. So whether A is positive or negative, I can just put the scheme and it would work in any case. So it's central. It's a central scheme. Well, and then maybe the third important aspect, which will keep us busy for a bit, is the fact that now the leading error term is actually very different. Again, if we go back to the, well, we can maybe go back here. So to the forward time backward space scheme, we have seen that the leading error term is some numerical viscosity times a second derivative. And that is a diffusive term. Well, now we are in a situation that the leading error term here, this is actually something, this is a term that is multiplying a third derivative. So that means that the leading error term is a third derivative. Now, of course, the question is, well, what is the behavior of a third derivative? For a second derivative, we said it's a diffusion. But for a third derivative, it's actually something else. And this is what we're going to discuss in a little bit later today in more detail. But let me just write that down first. So the leading error term from the modified equation, leading error term in the modified equation is, some alpha, some coefficient times uxxx, so a third derivative. And that actually gives rise to something that we call a dispersive behavior. And we will talk about that in more detail later. For now, I would just like to show you how a dispersive behavior looks like, because that's something that we will then see also in my MATLAB demonstration. So we do the same example as I had before. So if this is my if this is my initial condition, and I just let this one move, then at a later stage maybe that would be the exact solution. Now, a dispersive behavior now is that the solution would then look something like this. So, and then you would start to see wiggles around discontinuities. So these guys, these are wiggles or oscillations that appear in the solution, something like that. And this is a typical dispersive behavior. Well, what does that mean? Is, just to give a very quick explanation. Dispersion means that waves of different frequencies travel at different speeds, Well, and why is this a problem? Well, it's a problem because if you have sharp gradients, so for instance, like here, when you have the edges of this little top hat signal, well, if you think of that in Fourier space, if you have a sharp gradient in Fourier space, that means that a lot of frequencies are involved, and these frequencies, they have a specific phase relation to each other. Only if they're at the right phases with each other, you would actually see this sharp step. But now the problem is, if you then have advection, and this advection is such that different waves with different frequencies travel at different speeds, then these waves, they lose their specific phase relation to each other. So they kind of they run away from each other, and that's exactly what happens here, that you see all these different oscillations. So that's nothing else that the phase relation between the different waves has been lost because of the dispersive behavior. So that means then the advection leads to spurious oscillations, or as I said, wiggles. And that is a kind of a common feature for all schemes that are dispersive. And as we have just seen here, as soon as your leading error term is a third order derivative, so uxxx, then you would have this behavior. Now, why is this a problem? Well, the issue is that solutions that are dispersive, so solutions that have wiggles, they are not very, I would say, aesthetically pleasing. They don't look very nice. They actually look very bad. They look very wrong. At the same time, if you see a solution that perhaps looks like this, a diffusive solution, where kind of just sharp gradients are kind of smoothened out, they typically look much better. They look much more, continuous, or the solution looks much more continuous, looks much more smooth than the dispersive solution. However, we should keep in mind that dispersive behavior is typically obtained for schemes with higher order, so schemes that are actually would be of better accuracy than the first order scheme. But yet, the way that their solution looks like is maybe not exactly what we would like to have. And for that, there is a few techniques that can combine the advantages of the diffusive and the advantages of the dispersive, or I mean, the advantages of the first order and second order schemes, so that you get in the end a solution that is maybe kind of appears to be the nicest overall. Now, I would like to demonstrate that to you with a short MATLAB demonstration. Let me try to get that to work. It's always a little bit difficult to show that. I think I need to reshare the screen in the correct way, that you actually see my main screen. So let's try to do that. So I stop sharing this one and I add a complete screen. So I should be able to see the same screen as before. So what I'm going to show you here is a short MATLAB script. I can just briefly show it to you. So it's nothing fancy. It's a MATLAB script that solves or time integrates the Burger's equation. Burger's equation that we have looked at before many times. And what I would like to show it to you, or the way that I would like to show it, is that I start with a very simple initial condition, which I guess should. Now let's need to see what happens. Yeah. Okay. Now you should see it. This is a very simple initial condition. It was just a top hat signal, and I subject it to, or I run the Burger's equation with that initial condition. Of course, it's a top hat signal, so that means that I get on the right side I get a shock. On the left side, I get an expansion fan. This expansion fan at some point hits the shock, and then in the end, I just have a triangular signal that travels to the right. I can show that again maybe this is the best view that I can show it in this waterfall plot, which now doesn't. So yes, I think this now shows it in a nice way. So this is my initial condition that I had, this rectangular signal, and then what happens is that I get an expansion fan on the left side. So this kind of there's a triangular shape, which is kind of making the solution of this, or the length on top of the top hat signal smaller and smaller. Whereas I have also a shock here on the right, which travels with the Rankine-Hugoniot condition also to the right with a speed of 1/2, something like that. And then at some point, the expansion fan hits the shock, and then the shock speed slowly changes. This is maybe what I can see on this scheme, which I hope now it shows. That again, first I have a speed of 1/2, and then when the expansion fan starts to hit the shock, then I have a shock speed that is slowly changing, and so therefore it's a little bit curved, and then at some point it kind of becomes nearly a constant speed again. So this here is the exact solution of, or the exact solution, that's the correct solution of a top hat signal evolved using the Burger's equation. Okay, but now this is not what I would like to, or the main thing that I would like to show you. I would like to show you how different schemes are behaving using the for the Burger's equation. And what I have implemented here is 5 different schemes, and I will explain to you what they all mean. So the first scheme in blue, maybe I can make it big here, and I can show you here that the first scheme is the Lox-Friedrichs scheme. That is a scheme that we looked at maybe 2 times ago. That was also a central scheme, but it's only first order, but it is quite diffusive. Then we have the Lox-Wendroff scheme in green. That's exactly the one that I showed you now, the dispersive scheme. Then we have the upwind scheme in blue. That's just the first order forward time, backward space scheme. I've implemented here in the way that it takes care of in what directions the characteristics go. I have the McCormack scheme. That's not very relevant, but it's the same scheme that we'll use in homework number 4. And then I also have a kind of the best scheme, which is the flux limited scheme. And I will tell you in a second what the basic idea behind that is. But if you then look at the solution, which is now at a time 20, more or less, it's quite interesting to see how the different schemes behave around the shock. You can assume that the flux limited scheme, that's more or less the exact solution. So you have an expansion fan, so when the solution slowly goes up, and then you have the discontinuity here at location 7.4. So first of all, you see that the diffusive scheme, which is the Lox-Friedrich scheme, well, that is really diffusive. So this discontinuity is really just, it's not even a discontinuity anymore. It's just kind of a slowly rising hill, which is then kind of falling down again. So this is really the effect of strong diffusion in the Lox-Friedrich scheme. The upwind scheme, the light blue one, you can see it in here as well. That scheme is also quite diffusive, but not as much as the Lox-Friedrich scheme. But still, you can see that it starts already at this point slowly going down, and it's kind of more smoothened out than what you would expect from a real shock to happen. Then you have the Lox-Wendroff scheme, the one that we just derived. The one that I said is actually a more accurate scheme, but it has the problem that it suffers from dispersion. So you get wiggles. And I guess here you see very clearly what it means to have wiggles. Well, you see the green lines going up and down just before the discontinuity. And then, of course, this is something that we would aesthetically, we would say it's very, very bad. But in fact, it is actually more accurate because the position of the shock is much more accurately predicted using the Lox-Wendroff scheme as compared to the Lox-Friedrichs or the upwind scheme. And now the best scheme in this visualization is the red scheme or the pink scheme, and that's the flux limited scheme. And actually, we're not going into the details of how to implement that, but the basic idea there is that you try to combine the upwind and the Lax-Wendroff scheme in such a way that whenever you have wiggles appearing, you would switch back to the upwind scheme to have enough dissipation to kill all these wiggles, or making sure that these wiggles do not appear. So you would essentially have a sensor inside during your solution step that senses whether you start to get wiggles. And if you get wiggles, you would switch back to the low order scheme. And in those regions where you don't have discontinuities, where you don't have wiggles appearing, then you would use the high order Lax-Wendroff scheme. Overall, what happens then is that you get a very nice reproduction of the exact solution, which of course is now not shown, but you need to trust me that kind of the pink one is more or less the exact solution here. So it really follows the expansion fan up to the point when you have the discontinuity, then you rapidly go down, you have a clear discontinuity, and then you're zero again. So I guess this picture to some extent shows us what we mean with diffusive and dispersive behavior. And this we can all implement in a simple, in a simulation code, where essentially, for instance, you see here, this would be the Lax-Wendroff scheme. So this here would be the Lax-Wendroff scheme, and the flux limited scheme is actually not much more difficult. It's just, this would be the flux limited scheme. Okay, now what I would like to show you now to end up with this demonstration is a slightly more complex case, and it's again the Burger's equation that I want to use, which is a nonlinear equation, but I would like to show it to you with a slightly more complex initial condition. Now, what I need to do is I need to run it, and then I can show you the graph, the initial condition again. So let's just run it and not look at the result in much detail. I would like to show you the waterfall plot at the end, where we can see the results. That should now be prepared. So I again run the Burger's equation, but now for this case, and I guess you can directly see what my initial condition is. Turn it maybe properly. So this here is supposed to be my initial condition. So I have I'm 0, then I have one first step that goes up to 1, then it's 0 again, I have a second step that goes to 2, then it's 0 again, and then I have a region which is -1, and then it goes to 0. So this here is my my initial condition. So the idea is that I have a kind of a weak shock with a speed of where the height is 1, then I have a stronger one where the height is 2, and then I have also a negative one to demonstrate that my schemes can actually take care of forward traveling and backward traveling steps at the same time. And actually, okay. Now let's see what happens. What happens with this? If I just run it once more, let me just close all of this. We don't need it. So let me just run it. That you see. Well, you kind of see how this evolves, how the different shocks merge together. You can see again the green lines, which correspond to the Lax-Wendroff scheme, which is a lot of wiggles that are around. You see the kind of the diffusive behavior of the Lax-Friedrich scheme. But now, the last plots that I would like to discuss with you is essentially the space-time representation for exactly this solution. So we have x here and t in the vertical axis, And what I'm just showing here is the solution that I obtain as a function of space and time for the various schemes again. And if I'm just putting them, oh, that's not what I wanted. If I just put them next to each other, like this. So if I have now these four different solutions next to each other, and I guess we can directly see kind of the main differences. The Lux-free. So first of all of them give kind of the same solution. I mean, they're all convergent schemes. They're stable, and they converge to the right solution. They're all written in the correct way, so that I'm discretizing the conservative form of the equations. So I'm not doing kind of obvious mistakes. But I can see here that the Lux-Friedrich scheme is very diffusive. So the sharp shock is kind of lost very quickly. The upwinding scheme, you can see that it's also kind of a sharp interface, but if you zoom in, you can see that the interface is much less sharp than it would be for the flux-limited scheme, which I would consider to be the best and most accurate scheme. Also, if you look at where this position here is at the end, you can see that there's a slight difference between the flux-limited and the upwind scheme. The upwinding scheme is slightly slower because the shock speed is underpredicted. And then you have the Lux-Vendroff scheme, which is, if I start to zoom in, very, very wiggly. In particular, when you look here in this region, you see it looks quite terrible. Whereas the flux-limited scheme, if I'm doing the similar zoom in, trying to get kind of the same region, it is actually quite nice. So with this demonstration, I just wanted to kind of show you in real life what it actually means to have diffusive and dispersive behavior. So, and what it means to the solution, and how you can also then combine or construct schemes that, or a combination, or trying to combine the best of both worlds. So avoiding wiggles with the help of a diffusion, but still exploiting high order in those regions where you can. Okay. Right, then I see that there's a question here. There's a question: is there any difference between dissipation and diffusion, or can we use the words interchangeably? I guess we can use them interchangeably. I guess the difference is that diffusion is the process, and dissipation is what the effect of it is. So we dissipate kind of energy or fluctuations via having a diffusion. So I guess the correct expression here would be that the second derivative operator is a diffusion operator. So it diffuses the solution, and what effectively happens is that there's an energy dissipation. So we lose energy from, or kinetic energy from the system. But in terms of effect, it's the same. The difference really is between diffusion and dispersion. These are two, I would not say opposite, but these are two different types of mechanisms, which we will also look at in slightly more detail later on. Okay, so this is what I wanted to show you with this MATLAB code. Just write that down, that there was a MATLAB demonstration, if you want to look that up later on. And of course, if somebody's interested in that code, I mean, I can also share that so that you can experiment a little bit yourself. Okay, but I guess with this, we can actually already take the break, because I don't think it makes sense to start now with the stability before the break, but then in 15 minutes, we can then start with the second hour and look at nonlinear stability for these conservation laws. Okay, so with this, I pause. So welcome back to the second hour. as I said, now what we would like to discuss is again stability. You see, there's quite some focus on stability in various ways, but as you remember from the first lecture that we had together when we talked about convergence, consistency, and then also stability, it turns out that stability really has a key role in making sure that we actually get a good CFD result. So therefore, we need to kind of, we have this obsession with stability. But the problem is that so far we have only looked at linear problems, essentially. We have not looked at the actual nonlinear problems. And as you, if you remember, I mean, Navier-Stokes and also the Burgers equation in that regard is a nonlinear equation. So in principle, these equations are not, we cannot treat them with a von Neumann analysis, for instance, because that's only for linear problems. There is additional problems, namely coming from boundary conditions, and that is actually something that we don't discuss in this course. So we assume that the boundary conditions are always periodic for the things that we discuss. But of course that will give some complications, and this is then something what can be treated with more advanced methods. But what we can say for now is that earlier we have done the von Neumann analysis, and this was strictly only for linear problems. And the reason, I mean, the very simple reason why this is only for linear problems is that we actually went from a whole, so we did a Fourier transform, but then we considered each Fourier mode independently. And this is only possible for linear problems with constant coefficients. But now what we would like to do is we would like to look at a nonlinear problem. And actually it turns out there's not much we can do here apart from just linearizing about a convenient base flow or base state, and then just do the linear problem again. So in fact, this chapter here is maybe not extremely extensive. It's essentially just doing linearization. But let's do that step by step. So let's start with our nonlinear problem that we would like to consider or calculate the stability of. So we have something like this: u of t, ut is f of u derived with respect to x being 0. And with this, we can also write the quasi-linear form, which is the same in the continuous sense. So we have ut plus f prime of u times ux being 0. And now the issue is, because it's nonlinear, that this one is a non-constant. So that means in terms, so if we think of this as an advection equation, we see that we have advection with a varying speed, a solution-dependent speed. This is equation 1, and this is equation 2. So now the idea is we linearize, and we linearize in the sense that we assume that my solution u is some sort of base state, capital U, plus a small fluctuation. And this capital U we assume to be constant, and this guy would then carry all the fluctuations. So we can say that this is small perturbations. And this I can call equation number 3. Now, of course, I can put this equation number 3 into equation 1. So in my nonlinear problem, so what I get, if I just write it down, so we have ut plus u prime t plus f of u plus u prime derived with respect to x, and this is 0. And now what I can do is I can do a Taylor expansion of this guy. I do a Taylor expansion of the of f of u plus u prime derived with respect to x. So I do everything at once. So I can write that this f of u plus u prime x, that this is actually f of capital U derived with respect to x plus f prime of capital U times ux prime plus stuff that is actually of order u prime to square. Of course, the square should be inside the bracket. So like this. So this here is now a Taylor expansion of this nonlinear term. So that means if I put everything back and and I realize that either I can do it in this way, that I say that these two are independently zero because they're constant, or if I say that my base state U is just independently fulfilling also the Navier-Stokes equations, these guys together will drop out. So what I get in the end, I just what I retain is U prime of t, so this guy, plus this guy here, plus f prime of capital U times ux prime equaling 0. So this is what remains from the linearization. And now the beauty of this is that suddenly this factor, the f prime of capital U, now because it's the convection speed, but based on the base state, this is actually a constant. So I can say that this is a convection speed A, let's say. And with this convection speed of A, I have my fluctuation U prime that develops by means of an advection equation. So this is now maybe equation number 4. So I have a advection equation for the perturbations U prime on top of the capital U, which gives me that advection speed. And of course, now this is a linear equation. So now I can actually do a von Neumann analysis. So now let's just perform a von Neumann analysis. And I do that for equation number 4. So for equation number 4. And if I do that with an upwind, so example, I'll just take an upwind scheme, forward time, backward space, upwind scheme. Then I know, of course, for that I have A times delta t divided by delta x is lower or equal 1. I mean, this is what I know from the von Neumann analysis. And now, of course, because I know what my A is, that would mean for my specific case right now, it means that f prime of capital U times delta t divided by delta x must be lower or equal 1 for stability. Okay. So now I have translated the stability problem with linearization from a stability problem in U into a stability problem of capital U, so the base state. Now we're maybe not exactly at the end yet, because we could do a few more steps that are also, of course, all a little bit approximations, but that's what is typically done. In practice, I can now assume that not equals 0, of course, that the fluctuation u prime is actually small. So I mean, I'm looking at a small perturbation as compared to the base state. And of course, that would mean that this f prime of capital U, that would be, close to f prime of u plus u prime, because u prime is small. And of course, that in turn would be the same as f prime of my actual solution. So that means for this particular case here, instead of trying to get the stability with the convection speed of capital U, I can then say, okay, well, then let's just take a little u inside here. And this now would be the stability bound that I need to consider. So essentially what I did is I started with a linearization of the flow, and and then up to the point that I had a linear advection equation, I did the stability analysis of the advection equation, and then instead of taking the base state, the linear speed, the constant speed, I put back in the actual solution, so the f prime of u of my current solution, and that's what I'm using as the stability bound. So essentially, I'm just getting the local speed of the characteristics, wherever that is in the domain, so the f prime of u, and I'm using that in order to make sure that my speed is not larger than my grid spacing, if I think now of a CFL type of argument. Now, the important thing to remember here is that, or note or remember that this f prime of u, so the local speed, actually varies in space and of course also in time. So it changes as I progress in my simulation. So that means therefore take the maximum time step in the whole domain that is allowed. So the largest time step that I can take that is fulfilling the stability criterion in every point in the domain, because I only have one time step in the domain. I cannot, well, I can, but not in the framework that we look at here. I always have a constant time step in the whole domain. So that means in practice that my time step limitation, so my delta t that I'm using in the simulation, is lower equal delta x divided by the maximum of this f prime of u. So the maximum over j, and I'm now saying j is kind of all the grid points. So I need to evaluate what would be the time step allowed with the local grid spacing. I can maybe even have a j here to kind of make sure that I'm taking the smallest grid spacing in the whole domain. So I need to make sure that I take that grid spacing, that time step that is the largest time step that is fulfilling the criterion in the whole domain. So an example then, just to kind of make it more clear to you how this is really done. If we take the Burger's equation as a prototype of a nonlinear equation, there we have f of u is u squared divided by 2, and f prime of u is u. And if I'm using the upwind scheme as I was just saying, then my delta t, to do that dynamically, would be delta x divided by the maximum of the velocity or the solution u in the whole domain. If I assume that I have a delta x being constant. And of course, this maximum of u, that may be a function of time. So I mean, if you remember the example that we had before, the one in MATLAB, you saw that in the end, I just had an expansion fan where the maximum got lower and lower. That would mean that my time step would then become progressively larger, or the maximum possible time step would become progressively larger. So this is the way that it would work. And if you now compare to what kind of compare to the CFL condition, if you remember, what I said there was that kind of a sloppy interpretation of the CFL condition is that the solution may not, or the information may not travel more than one grid point. Well, that's kind of what you see here, even in the nonlinear case. I have the grid spacing, delta x, and I have the maximum velocity. And this should just not be, so the time step should be such that I'm not traveling more than one grid point. That's essentially what is expressed here. So compared to CFL, the information should not travel more than one grid point. That's essentially what comes out here. And that is a local measure depending on the local speed in your whole domain and the local grid spacing that you have. And this type of calculation is done in every CFD code. At some point, you will compare, or you will calculate this local speed, or the local grid, the local speed and the local grid spacing, and thus the local time step in every point. And then you will do a global reduction operation, and you will take the global minimum for the time step that is the maximum time step that is stable everywhere. And that's an operation that is done in every CFD code at some point. And at times it may be an expensive operation because it's a global communication. You need to collect the grid spacings and the speeds from all different processors or parts of the domain. Okay, so this was a nonlinear stability. As I mentioned a few times, it's actually not a very fancy thing. It's just doing linearization. That's as much as we can do. Okay, now having said this about nonlinear stability, I would like to continue now, essentially going back to dispersive and diffusive errors that we were talking about before, but I would like to give you a little bit more detail on how to do the analysis and to understand why these things actually appear, and then show you an alternative method on how to control these errors. And that will also be the last topic that we discuss, or the second last topic that we discuss together. So that is chapter C2, and that is dispersive and diffusive errors, as we have seen before, but just with a little bit more detail. As a motivation, I'm just drawing these two figures again. If you remember, we had, this was the initial condition, then we have the advection equation. If this is x, then we have the advection equation that does this. And if I'm just being lazy and I'm just copying this, so if I just have these two diagrams, and if I plot in the upper one, I plot diffusive errors, then the solution would probably look like this. And if I have dispersive errors, it would probably be like this. So this was diffusive errors, and these were dispersive errors. So what we would like to do now during the next few minutes is trying to understand from the equations why a second order term. So uxx, for instance, gives the diffusive behavior, and the uxxx gives you a dispersive behavior. Because I think in the end, this is quite instructive, that you can see that this is really not a coincidence. This is just what really comes from the equations, and this is something that we can understand from looking at the essentially Fourier decomposition of a solution. So to further understand these phenomena, let's consider a single wave. So a wave solution, which maybe has the form like this: U is U hat times e to the I kx minus omega t. So this would be the way that I would typically write a wave. There's slightly different conventions, whether or not you include the omega or the k inside the I or not. But this is kind of the way that I prefer it. And what it means, if I'm plotting this in a space-time diagram, just to give you the kind of the connection to a solution in physical space. So if I have a wave like this, that would correspond to wave crests that are distributed like this. So this would be the wave crests. Of course, between the wave crests, you would then also have the corresponding valleys, or the minima between. Now, so that means if you stand at a fixed position in x, and you just wait, so you advance in time, then you see that there's a first wave coming, then a second wave, then a third wave is coming. And these waves, they of course have a distance in time, which I call capital T, and that would be the period of the wave. And this period, of course, as you all know, is related to the omega, which is 2 pi divided by omega. This is the period of a wave. If I'm standing at a fixed time, and I just look at my domain, then of course I see again many waves, wave crests here, 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 and here, and the distance in space between two wave crests would then be the length L, which I would call so this is 2 pi divided by alpha by k, with the notation that I'm using here. And this would be the wave length. This k here. Okay, so far so good. I guess that's nothing new to any of you. But now I can, of course, define a speed of this, or I can define various speeds of this. So first of all, I can define the speed of each individual crest. That essentially is how fast one crest is progressing in space. And that is the so-called phase velocity. And that is nothing else than just omega divided by k. That's really just the slope of this yellow bit. I can, however, also define a group velocity. And the group velocity would be the speed that you would assign to a wave packet that is living inside, or that is composed of different individual waves. So this is how the speed that a group of waves would travel with each other. And the phase speed might actually be larger and smaller than the propagation speed of this whole wave as a whole. This group velocity, Cg, is then defined as the derivative of d omega dk. So I guess you're all familiar with these expressions. The reason why I'm introducing them or summarizing them here is because they come actually in quite handy later on in understanding the features of these waves subjected to different types of terms, which then allow us to understand how dispersive and dissipative errors actually arise. Okay, so now we have the basis for these waves, and now let's just try to see what happens if we actually apply them to some of our equations. So we start with the advection equation, and the advection equation, of course, is ut plus lambda. Well, now I take lambda times ux. Here I take lambda because that's maybe the slope of the characteristics, but I mean I could take my typical a here as well if I wanted. Now the question is, how does a wave react to being advected by the advection equation? Well, how I can find out is that I just take my u from my wave and I put it in here, and I will see what happens. Well, sorry. So what I get then is u hat e to the ikx minus omega t, but now I need to do the derivative with respect to t, so that becomes minus I omega. And this is equaling minus lambda e to the ikx minus omega t. And again, I need to do the derivative, so I get an ik here. And of course, now most of the things fall out, and what I'm ending up with is omega is lambda times k. Okay. Well, now I know that, or now I have found a relation between omega and k, and this is actually something that is called a dispersion relation. So that essentially means I have an omega as a function of k. So I relate the frequency to the wave number. And I have now found a specific dispersion relation for the advection equation. Now for the advection equation, I can now use the expressions that I have written down here for Cp and Cg. And perhaps it comes to no surprise that the dispersion relation for the advection equation simply says that Cp is lambda, and there's also Cg. So that means what I have here, what I found for the advection equation is, well, the phase speed. I found that the phase speed and the group velocity of a wave that I put into the advection equation is traveling with a constant speed lambda. And of course, that means that I can write down now the exact solution. U of x and t is u hat times e to the ik x minus lambda t. Well, what I see is, what my solution now shows me is that my wave is just moving with a speed lambda. And of course, you can say, well, this is not extremely surprising, and we have done that, many times before. And of course, that's true. I have an advection equation, so my solution advects. So there's nothing really surprising with that. Advection with speed lambda, as expected. Okay, there's a question. Can you please explain what U hat is in this context? U hat in this context is just the amplitude of this this particular wave. So what I did is I just consider one wave in space and time as I sketched here, and of course this wave has a certain amplitude. That's it. And what I see here in my exact solution, when I put this into the advection equation, I see that of course this amplitude is just remaining there. So this is a truly hyperbolic problem in the sense that I just, I have a translation, a wave-like translation, but no change of amplitude. Okay, this was maybe not extremely surprising or extremely exciting, but now I think it becomes more interesting because we can start to see what happens if I'm now going for a second order and the third order equation. So if I'm going to the second order equation, which the prototype would be the heat equation, well, ut is nu times uxx. Well, I do the same type of analysis. I just take my wave solution, I put it in order to calculate a dispersion relation. So as above, I get then as a dispersion relation the following. I get omega is minus I nu k squared. And my solution then, my u of x and t would then be u hat times e to the I kx times e to the minus nu k squared t. And now it's of course a bit more interesting than for the advection, because now we actually see that my exact solution actually has two parts. I have one part here, which is clearly an oscillation, because it is in IK, so that means there is a spatial oscillation. But then I also have a second part, which is e to the minus nu k squared t. And this k squared here is a positive number because it's a square. So it's certainly positive. And nu is positive, time is positive, and there's a minus sign in the front. So that means that this is something that is an exponential, which is getting smaller and smaller as a function of time. So that means that I have this last term together with the amplitude means that my amplitude actually decreases exponentially in time. But I do not have any wave propagation in space in time anymore, because there's only an IK, but there's no omega left in there. So that means that the actual solution to a heat equation is no wave propagation. There's no wave propagation there. My Cp is minus I nu k, so it's actually imaginary. And my Cg, the group velocity, is minus 2I nu k. Also, that is imaginary. So therefore, there's really no wave propagation, but at the same time, I have exponential decay in time. I mean, provided that this nu is larger than 0. And of course, also here you may say, that's not so surprising, because that's exactly what we discussed when talking about parabolic equations, which the heat equation is an example of. There's no time, there's no wave-like behavior, but rather a diffusive behavior due to this exponential decay. And of course, that's exactly what I would like to demonstrate here. So as soon as you have a second derivative here, you will get this exponential decay in time. So you will get this smoothing out of waves. And that's exactly the reason why we see also a diffusive behavior as soon as your leading error term is actually of second order, or has a second derivative, I should say. Okay, but now maybe the last step, which is probably the most interesting here. Now we would like to find out what happens if I actually have a third derivative, because that's the leading error term that I had for my Lax-Wendroff scheme. And I'm doing this whole thing to understand what really the behavior of this third derivative is. So the equation for the example would be the one of a dispersive wave. So if ut is alpha times uxxx. That's the test equation. And I'm again doing the same analysis. I'm just taking my my ansatz, I put it into this equation, and then I derive my dispersion relation. And my dispersion relation becomes looks like the following: omega is alpha times k to the power of 3. Then I think now is quite an interesting result, because I can again calculate my CP, so my phase velocity. My CP now becomes alpha times k squared. And my CG, my group velocity, becomes 3 times alpha k squared, or 3 times CP. My exact solution, u of x and t, would then be something like this: u hat of e times e to the ik x minus cp, as cp times t. That, of course, is exactly the same as I had for the advection equation, but with cp being alpha times k squared, as I just wrote. Now, what is the importance here? Well, the importance is that I get a CP that is depending, or the CP depends on k. So that means the speed with which my waves travel is actually dependent on the wave number k. And in this case, it would actually mean that shorter waves, so that means higher k's, they travel faster than lower or longer waves. And of course, that's exactly what we have seen before when looking at the effect of a dispersive term in this particular case. The exact solution would be that I would just advect everything, all the waves with the same phase relation, with the same speed. But now it turns out that if I have a dispersive term, so an uxxx term in my equations, then suddenly it is like that not all waves have the same speed. So the difference in speed depends on this prefactor alpha that I have introduced. So this prefactor alpha tells me how much the speed actually differ, or gives me a quantification of my speed. And of course, this alpha, now if you think back to the Lax-Wendroff scheme, we can maybe directly go there and look at it. That was here. So this guy, which now I can call alpha, this guy is dependent on numerical parameters. You see here that there's a sigma inside. So by choosing my delta t and my delta x, I can actually adjust what this alpha is. So it turns out I can kind of see whether I get a large factor or a low factor, depending on my CFL number. And here I see now that the reason why I get this dispersive behavior is exactly because I break up the idea that all the waves travel with the same speed. So the reason why I showed you all this is because by this Fourier analysis, you can actually understand why certain schemes give certain types of errors. And this we can all see with this modified differential equation approach. So the modified differential equation gives the leading error term, or provides the leading error term, and this guy in turn determines or indicates the behavior of the solution. Behavior of the solution. And typically what we get is if we have an upwind scheme, so that is a first order scheme, then typically what we have is that the error can be then written as a second derivative, and this will give you a diffusive behavior of the solution. So your leading error term acts as a diffusion, which will lead to kind of smoothened out solutions. And an example, of course, is the typical upwind scheme that we have seen, irrespective of whether we do this flux splitted scheme where it would work from both sides. The underlying discretization is still a first order scheme. And then, as I said, you get a diffusive behavior. If, on the other hand, you have higher order schemes, so for instance, the Lax-Wendroff scheme, which is then a second order scheme, and the leading error term is then of third order, so UXXX, then you get a dispersive behavior. But this is kind of a common thing that first order schemes, they have a diffusive behavior, and then second order schemes, they have more a dispersive behavior. And in some sense, this also kind of explains why that under certain circumstances, it's actually very difficult to stabilize second order schemes or schemes where you have gotten rid of the diffusion term. So just think of the central scheme that we have constructed from the first order scheme. The second order scheme is or was constructed in a way that we can get rid of the second derivative in the leading error term. So that's why we then got the second order. But of course, the problem with that is exactly that you have lost all the diffusion in the problem. And then that might lead to the fact that it becomes unstable. And then we could then stabilize it again by adding this a controlled dispersive behavior as we did for the Lax-Wendroff scheme. And that kind of indicates also a little bit how we could kind of, combine these schemes together such that we get the best of both worlds. As we said, we don't like wiggles. Wiggles, nobody within numerics or CFD likes wiggles. So we would like to get rid of the wiggles, but sometimes wiggles only appear in those positions where you have sharp gradients. And if you have not so sharp gradients, you actually don't get wiggles and you get actually the benefits of a high order scheme. So therefore, now the idea would be to combine, or maybe not to combine, but to control wiggles with a, well, that's now very bad English, control wiggles with a controlled diffusion at those places where it is needed. Where needed. So for instance, if you now take again the example that I just showed, where we have this was the exact solution, and now my kind of second order scheme would maybe look like this. Then I would make sure I would like to have a method where I could identify where these wiggles are, preferably before they arise, and then just add a diffusive operator just in that region where I have the wiggles to control and reduce the amplitude of these wiggles. And this is an approach that is called artificial viscosity. So that is the idea that we produce viscosity in an artificial, so we do that explicitly, but only in those regions where it is needed. And this is something that I would like to show you, unfortunately not today, but tomorrow at 10, very briefly before we then do one last look at the boundary conditions. But this is one way of controlling it. The other way that we have seen today in the example that I showed you with a flux limiter, this is something we're not going to discuss, but I'll maybe say a few comments on that later on. Okay, but this was all I wanted to tell you for today. And as I said, tomorrow we just continue here how to combine these schemes, and then we will then soon conclude. There is the question, when will be the next homework be uploaded? I would now say it should have been uploaded already, but if not, I'll check why this has not happened yet. But it will happen soon, I guess tonight then, if it's not yet there. Okay, thank you very much for today, and have a nice evening, and see you tomorrow.